that we'll be recording. All right. So don't think I've seen either of you before. So how let y'all know, I'm an instructor of 1080 as well. And my goal for today is just review the topics in test theory and to work through some problems together to see how well we understand the material. So before we start, which topics would y'all like to go over first? And we'll kind of work our way down, kind of get a head start.
Sorry, could you repeat that? I wasn't listening.
Sure thing. Are there any topics that y'all want to start with first to review?
Remainder theorems with the Taylor remainder theorem, just applications with it, I think.
Okay. Taylor remainder theorem. Okay. All right, Celeste, what we're doing right now is we're listing topics that we're going through. So right now I got Taylor remainder theorem as a topic to discuss. What other topics we all like to discuss? That'll be on test theory. So kind of
limit comparison test, harder problems with that.
Okay. LCT. I'll put DCT as well to go with it. All right. What other topics go with that?
Manipulating power series.
Okay.
With like I don't know, to make it look like a different one.
Got you. You're talking about like, here's a power series of blah. Do the thing to get a blah.
Yes.
Or something like that.
Or like,
perfect.
Given this power series, yeah.
Perfect. Can you do that? All right. So far for topics to discuss, I have Taylor remainder theorem, in particular for series tests, limit comparison tests, and manipulating power series to get a new power series from that. Any other topics that y'all want to go over afterwards? Okay. So I think we have 3 right now. So I think that's enough to get started. And once we do more problems with it, we can add to the list. So with that, let's go ahead and share. And let's get started. So first thing with the Taylor remainder theorem. Before we start doing problems, let's do a recap of it and kind of talk about the hurdles and how to typically solve this stuff, these things. So recall from Dr. Bird's notes that if I want to estimate the remainder of approximating a function with an nth order Taylor polynomial, I am going to get that by m times the absolute value of any input x minus the center that I'm basing my Taylor polynomial on, raised to the n plus 1 power divided by n plus 1 factorial. And to give a recap, I get m by bounding whatever the n plus 1 derivative of f is. That's how we get what m. So, main thing I'm going to say, the hardest part about these types of problems is figuring out what that number or constant m is going to be. So I'll make that as a list. So when finding that estimation for the remainder, figuring out what that constant m, that's going to be the hardest part for these types of problems. I'm trying to figure out what m is going to be. The general steps, kind of a way to tackle how to calculate and how to do these problems is first thing we need to do is we need to figure out what the nth plus 1 derivative of the function is. So first step, determine what the nth plus 1 derivative of f is. So I need to take derivatives in order to discern what that's going to be for that. The next step, and typically this is going to be the part that helps figure out what a good candidate for m is, to determine if that nth plus 1 derivative is an increasing or a decreasing function. That's going to be one of our goals to help us figure out what will be a good candidate for m, is to determine if that nth plus 1 derivative, whatever I get, is an increasing or a decreasing function for that. The best way that I'm going to do to get that is by using first derivative test. Which means I'll have to take one more derivative. So if I already took the f plus 1 derivative, I'll need one more derivative. And first derivative test says if it is positive, then the original function is increasing. If it is negative, then the previous function is decreasing. Now, the reason why I want to know if this function is increasing or a decreasing function is because typically when you are doing a Taylor polynomial, you're doing this with your s values being in an interval that I'll call b to c. And what step 2 is going to tell you is going to tell you which of those endpoints in my interval b to c I'm going to be working with. So if I get that my function is an increasing function, then what's going to happen is my values will not get larger than if I plug in the right endpoint for that nth plus 1 derivative. Why is that? Well, in step 2, we concluded that if it was increasing, then that means as my outputs get bigger, my inputs get bigger, my outputs will also get bigger. So that would mean that for any value for x in the interval b to c, it will not get larger than if I plug in the right endpoint into my nth plus 1 derivative. And so that's the case if it is increasing. Vice versa, if it was decreasing, Decreasing function means as my inputs get larger, my outputs get smaller. So if you conclude from step 2 that the n+1 derivative is decreasing, you get your largest value by plugging in the left endpoint. If you concluded from step 2 that the n+1 derivative is decreasing. And the reason why I'm emphasizing that is that will be our potential candidate for M, whatever number I get as the output for that. So that's why I want to exploit step 2 and know whether or not the n+1 derivative is an increasing or a decreasing function. Because I want to exploit that fact and get a potential candidate for what M is going to be. And once you get that potential candidate for M, we get to profit. And we get to be like, okay, now I go back to my original inequality, work from there, and profit from it. So go back to Blue Star and profit from that. So that's going to be our major goals for YETS. Now for step 3, there are a couple of exceptions for that being a potential candidate for M. One exception is if f of x is either sine or a cosine. And the reason I want to put these two on the side is because if I take, say, derivative of cosine, I'm going to get negative sine. And one thing y'all saw in Cal 1 is that no matter how many derivatives I take of either cosine or sine, I'm always going to bounce back and forth between the sine and cosine. I might be off by a negative sign, but I'm going to be bouncing off from them. So I'll emphasize that down here, that derivatives for them are either plus or minus cosine, plus or minus sine. And now the reason why I'm emphasizing that is because it makes the n+1 derivative a little bit smoother to calculate. Because let's say my function is either a sine or a cosine. Well, if my function is either a sine or a cosine, then that n+1 derivative will either be a plus or minus sine or cosine. And the thing about sine and cosine is that no matter what input I plug in, sine and cosine can never get larger than 1. Which in that case, I don't have to check increasing or decreasing. I can use that fact, set 1 to be M, and then move on. So I want to mention that that is that one major exception, that if you have sine or cosine as your function, then you can skip through steps 2 and 3 because your derivatives will always be either cosine or sine, and you're never going to get larger than 1. And that'll be our candidate for M immediately. All right. So that's going to be our game plan in general, how to find the remainder estimate for a Taylor polynomial. Now let's do a problem to try to illustrate that. So before I move on and give y'all some problem to work on, does anyone have any questions about kind of our steps of how we tackle it? Okay. So with that, let's go ahead and let's do a practice problem with that. Try to play with it. So with that, let me go ahead and pick a problem for y'all so you get y'all started. And while I'm getting a problem set up and ready to go, if y'all have questions, let me know. I'll be happy to answer. Okay. Perfect. So the problem that I'm going to first recall from this, I'm pulling this from an older exam. For reference, the problem that I'm pulling up comes from the fall 2018 exam, and this is multiple choice 8 for that. So here's the information that we have for it. I'm going to let P1 denote the Taylor polynomial. For cosine of x at my center being at pi over 3 for yes. And so what we are going to try to estimate with this is we're going to try to select the best bound for P1 of s being an approximation on the interval 0 to 2 pi over 3. And that's our goal for that. So let's walk through a solution and how we tackle it. First, let's go ahead and do some bookkeeping because that will be useful for us to keep track. First, I want to identify f of x, or the function that we're trying to take the approximation of. In this case, you're told by the problem that we're trying to find the estimation for Taylor polynomial for cosine. So that will be our f of x. So f of x is cosine. For n, even though we were not explicitly told what n was, we were already told that we're taking the first order Taylor polynomial to approximate cosine. And so because of that, that tells us that n is 1. We are also told that our center for this Taylor polynomial that we are working with is going to be at pi over 3. So that's what we're basing our approximation on at Taylor polynomial. And the interval that we are working with for all values for x to be plugged in is at 2 pi 0 to 2 pi over 3. So let's scroll up. There we go. So here are some of the bookkeeping that I'm going to use for that. So based on what I got, what should I do to try to get m, or try to figure out what that m would be for that bound? So that's what I'll ask y'all to do right now. What will m be here? Okay. Okay, that's fine. Thanks for letting me know. You can post in the chat. Go ahead, Zachary.
I do have a quick question. It's just because I came in a few minutes late, but why is your n going to be equal to 1 because of f of x cosine x?
So we were told at the beginning that we are using the first order Taylor polynomial. And so when we were doing the Taylor estimation theorem, our n, or what that will be for the estimation for the remainder, that n located here has to match the order of the Taylor polynomial. So because we're given a first order Taylor polynomial, that tells us that n has to be 1 for that guy.
Okay, thank you. That makes sense.
You're welcome. All right. I got in the chat that would n be 1? It would be. Bingo. Let's go back. Remember, keep them, in this case, we do have one of our exceptions. And we have cosine here. And so let's write down that below. That since the function I am working with is cosine, that means it's n plus 1 derivative, which in this case will be the second derivative will be a negative cosine of x. And if I put that in, sine and cosine has a nice feature where no matter what I have in as my input, it can never be larger than 1. So as mentioned in the chat, for this problem, n would equal to 1 here. Okay, before I move on, any questions about how we got m for this problem?
I do have a question.
Hmm?
So I see that you put the 1 in for the n to make it, is that saying that that's a second, what is that denoting right there? The f of 2 of x is equal to negative cosine of x.
Same thing as saying second derivative.
Oh, okay.
Yeah, I just put the 2 in there to note that this is the second derivative of f of x.
Okay.
This is, yep. Problem. Just keep in mind that if you're not able to speak, you're able to use the chat as well, and I'll keep it up on my other monitor to make sure that I'll read it on my end. So if you do have a question, you want to type it out in the chat, I'll be able to see it on my other monitor. Okay. So now that we know m is 1, let's get that remainder. So the error, or the remainder, of estimating cosine with the first order Taylor polynomial is less than or equal to m x over the center n plus 1 over n plus 1 factorial. We can go ahead and do some changes to this formula. First, we know what m is. We know m is 1, so that replacement can go now. Second, we know that the center of my Taylor polynomial is pi over 3, so that goes away. And we also know that n is 1, so I can erase the n and replace it with 1 now. Simplifying, what I get now is x minus pi over 3 inside the absolute value squared over 2 factorial for that. Okay. Keep in mind that we are working within the interval 0 to 2 pi over 3. Now, with we're estimating the remainder, I'm not done here. And that's because I'm not given a fixed number anymore. I still have that x I have to worry about, which could be anything so long as I plug in a number in that interval. So we need to get around that. And the way we're going to get around that is to something similar that we've done to in general, when we talked about checking if the n plus 1 derivative is usually increasing or decreasing. You're welcome. Saw that in the chat. Welcome, Jasmine. And that is the fact that I have an x squared. And that is, and the fact is, an x squared is an increasing function on this interval that I'm working in. If you wanted to prove that and verify it, first derivative test, derivative is 2x. If you plug in anything from 0 to 2 pi over 3, the derivative will always be positive, which means that the original is increasing. And the reason why I am mentioning that again is because I can get rid of that x by changing and writing as my next bound a less than or equal sign over the right endpoint. Because keep in mind that if I am an increasing function on my interval, I will obtain my largest value if I plug in the right endpoint to the function itself. So for the remainder theorem, I can get rid of that x that's chilling when you're setting it up by bounding it, getting a less than or equal to, as if I'm plugging into the right endpoint. For notation, note that I do need a less than or equal sign here, because I am saying no matter what value for x I plug in, yes, that has the yellow dot beside it will always be smaller than if I plug in 2 pi over 3. So I'm displaying that fact to effectively get rid of that x for my remainder estimate. And then after we do that, we now evaluate. 2 factorial is 2. 2 pi over 3 minus pi over 3 is pi over 3. That's already positive. So the absolute value becomes redundant. Pi over 3 squared is pi squared over 9. Fraction in the numerator divided by another number. That's the same as multiplying those denominators together, giving me a final answer of pi squared over 18. And that gives me a bound for the remainder estimates for that guy. So, any questions about any of the work here? And I'll scroll back up to show the beginning steps along with the problem statement.
For the, when you said that the x squared was increasing on 0 to 2 pi over 3, if we had seen that something was there that was decreasing, would we then use the leftmost bound?
You're correct. Nice thing is, because of the absolute value, you don't have to worry about that. You'll guarantee that increasing function no matter what. But technically, you're correct, Zachary, that if I concluded that was decreasing, I would plug in the left endpoint instead of the right endpoint.
So with this type of problem where, because of the absolute value, we're probably always going to be using that rightmost endpoint.
Right.
All right.
Real quick, how do we know that our m equal to 1?
N equals to 1. You know that, Fritz, because we were told at the problem that we have the first order Taylor polynomial that we use to approximate cosine.
I'm sorry, I meant m.
M, perfect.
Yeah.
Thank you. So because our function is cosine, the nth plus 1 derivative, no matter how much I work for it, will either bounce back and forth between sine and cosine. It could be off by a sign, but I'll bounce back and forth. In this case, since n is equal to 1, I'll be taking the second derivative, which will be negative cosine. And the nice thing about that is no matter what I have here as my n plus 1 derivative, whether it be 4, 5, or 6, or 100, because my original function was cosine, nice thing about cosine and sine is no matter what I have inside the function, sine and cosine will never be larger than 1. And so because of that, I'm going to exploit that fact, and I'm going to set that to equal to m, and that's how I got it.
Okay, thank you.
You're welcome.
Would that ever be anything other than 1? Because if we were doing with sine, it could never be anything greater than 1, correct?
Got that in the message. I'll be doing that as my next example. But Zachary, to answer your question, in general, what we will have to do is we will have to determine if I have an increasing or a decreasing function and exploit that fact to help us get a bound that would serve as our candidate for m in that case. So in general, we could have bounds that are not 1. And in general, our game plan is we're going to take that nth plus 1 derivative, and we're going to determine if it is increasing or decreasing. And if we determine if it's increasing or decreasing, we're going to use that and exploit it to try to give us a bound for M in that scenario. And so the next problem I want to work on, it will be us doing one where M is not 1, and us going through that. Thank you. All right. Any other questions about this problem in particular before we move on for another guy? Okay. And so I got in the chat that, yep, we need to, let's do something where I don't have an M equals 1. So let's do it this way. Let's say f of x is now, and let's go down to here to get that scroll. Let's say f of x is now x times the natural log of x. And let's say that what I want to do now is I want to use the third order Taylor polynomial. So P3 of x centered at 1 to approximate the function. And our goal now is, okay, what's the error or what's the remainder of me using n? And so I'm going to go ahead and let y'all know that this is one example where m is not going to be 1. So we're going to tackle it using our normal process for yes. I'm going to take the m plus 1 derivative, determine if that is an increasing or a decreasing function, and exploit that to help us get a potential candidate for m. So let's do that. First, let's do bookkeeping. Strike down f of x. Here, you're told that we have the third order Taylor polynomial, which tells me that n in this case will be 3. In this case, our center, we're told that we centered at 1. So a in this case will be 1. And so now that we have that bookkeeping is stored, let's walk through our general steps to find and get the bound for the estimate. First step, you have to find the f plus 1 derivative, and because n is 3, that means we need the fourth derivative of f of x for that. So for my function f of x, which is x times the natural log of x, and if I ask, oh, okay, take its first derivative, what will that first derivative be?
One.
So be careful for 1. That'll be part of it. If you keep in mind that this is a product of 2 functions.
Is it just natural log?
You're close. Let's go through that. So we have a product of 2 functions here. where my first function is x, second function is natural log. So that means to get its derivative, I'll need to use the product rule for that. Product rule says derivative of the first function times the second function plus the first function times derivative of the second function. Derivative of x will be 1. So I have natural log of x. Derivative of natural log will be 1 over x. The x's will cancel, leaving me with 1, giving me natural log of x plus 1. So y'all had the separate pieces, but we did need to combine that natural log and one that y'all mentioned to get the full first derivative, since we do have a product. Any questions so far about that? Now I need to march forward. Take the second derivative. Second derivative is the derivative of the derivative. So that means we want to take the derivative of natural log of x plus 1. And if I do that, derivative of a sum and difference is the same as me saying take derivative of each proponent, then add them up at the end. Derivative of natural log will be 1 over x. Derivative of 1, since that is a constant, that would be 0, giving me 0. So I just have 1 over x. And on purpose, I'm going to write that as x to the negative first power, because that will be helping me figuring out what the third derivative is. So if I now know that the second derivative is x to the negative first power, what will the third derivative be?
Would it be negative squared?
Exactly right. By power rule, take the old coefficient, move it as your new coefficient, and then subtract 1. Very good. And now to the fourth derivative. If I now know that my third derivative is negative 1 over x squared, or negative x to negative 2, what will my fourth derivative be?
One over x cubed.
You're close. Keep in mind that I do have my old exponent to be negative
Oh
2.
yeah, two over x cubed. My bad.
No, you're fine. You're perfectly fine, Fritz. All right. With that, here's our guide that we're going to use to help us figure out what m is going to be. Any questions so far about step 1 of finding the bound for the remainder. Okay. So there's step one. Step two now is going to be determining whether or not my fourth derivative, which we now know is 2 over x cubed. We want to know if that is an increasing or a decreasing function. I forgot to say what the interval was. I just realized that. But the interval we're working with, let's say it is 1/2 to 3/2 for yes. So our next goal is to determine if the 2 over x cubed will be an increasing or a decreasing function in the interval 1/2 to 3/2. And so let's figure that out. To help us figure that out, we're going to use the first derivative test on the function 2 over x cubed. Because as mentioned before, first derivative test, we're going to take one more derivative. If it is positive, I increase. If it is negative, I decrease. So let's do the work down here. So we're taking derivative of 2 over x cubed. To avoid using the quotient rule, I'm going to use x to the negative cubed power. Now it is a power rule problem. 2 is an extra coefficient. So our derivative rule says, if I have a coefficient in front of the function, I can move it out of the derivative and then take the derivative of what's left over. Derivative of x to the negative cube by the power rule will be -3. Start my 3 to be a little bit pretty. There we go. X, subtract one more exponent, giving me an x to the 4th. There we go. Multiply the coefficients. I have -6 times x to the negative 4th. Which equals to -6 divided by x to the 4th power. So with that, in my for all my values of x between 1/2 and 3/2, well, -6 divided by x to the 4th, will that always be positive or will that always be negative? Bingo. See some in the chat. Some of y'all saying negative. Y'all are right. One way to justify why. I have a 4th power in my denominator with x. So that means no matter what I plug in, denominator will always be positive. But because of that negative sign, that tells me that I will have positive divided by a negative, which will be a negative. So first derivative test tells me that the derivative of the of 2 over x cubed will always be negative, which means that 2 over x cubed is decreasing on that interval. So let's say that now. So by the first derivative test. Our function for the fourth derivative, which was 2 over x cubed, we got and showed that it is decreasing on my interval 1/2, 3/2. Now, why is that important that we know it is decreasing? That tells me that 2 over x cubed is going to get its largest value if I plug in the left endpoint of that interval. So in other words, 2 over x cubed will obtain its largest value if I plug in 1/2. Because of that, I can now do the following. Found the absolute value of the fourth derivative of x, which we got to be 2 over x cubed. We can now say this would be less than or equal to the function as if I plugged in the left endpoint. 2 over 1/2 cubed. Numerator and denominator will always be positive, which makes the absolute value now redundant. So I have 2 divided by 1/2 cubed. 2 cubed is 8, which means 1/2 cubed will be 1/8. Dividing by the fraction is the same as multiplying by its reciprocal, giving me 16 in the end. And that 16 over here, I have a less than that fourth derivative. That gives me my candidate for M, which is 16. Any questions about that step or anything I need to clarify? Again, for I noticed that 1 or 2 people have popped in. So I'll summarize again. Remember, goal to find a candidate for M. Once you know the M plus 1 derivative, check if it is increasing or decreasing, which means you will typically use the first derivative test. Check if that derivative will be positive or negative. Here we determined that it is decreasing, which means that I will get the largest value if I plug in the left endpoint. So that means for all values of x, absolute value of 2 over x cubed will be less than if I plug in 1/2. And once we simplify, we got that to be equal to 16. And that would be our candidate for M for this problem. So before I move on to the next step, which is to finish up and get the remainder, any questions on step 2? Okay. And now we bring it home. Now we're estimating the remainder using the third Taylor polynomial. In general, that is less equal to M, absolute value, x minus a to the n plus 1 power over n plus 1 factorial. And keep in mind that the interval we're working with is 1/2 to 3/2. Because of our work from steps 1 and 2, we can go ahead and do some plug-in substitution. First, we know that m is 16, so I can erase that m and replace it with 16. Second, I know that my center was 1, so I can erase a and plug in 1 for that. And I also know that I'm taking the third Taylor polynomial for the approximation. So I can get rid of n and replace it with 3. Now let's simplify that. That means I have the bound to be 16, absolute value, x minus 1 to the 4th power over 4 factorial. Keep in mind that I'm working into interval 1/2 to 3/2. As mentioned in the previous problem, I don't like the fact that I have an x here because that's not fixed. I want to get rid of that x. And the way we get rid of that is to note that that absolute value raised by some exponent will always be an increasing function, which means anything in that numerator is going to be less than if I plug in the right endpoint of 3/2. So for my next line, I replace the equal sign with a less than or equal sign and plug in, instead of x, 3/2 for here. Stay blue. Minus 1, 4 factorial. And now we try to simplify as much as we can. 3/2 minus 1 will give me 1/2. Absolute value of 1/2 will be 1/2. So absolute value is redundant. So I have 16 1/2 raised to the 4th power over 4 factorial. 2 raised to the 4th power is 16, which means that 1/2 raised to the 4th power will be 1 over 16. All that divided by 4 factorial. Now, over here, I have 16 multiplied by 1 over 16. So I'm multiplying the reciprocals with each other. So the 16s are going to cancel each other out, leaving me overall the numerator with 1. So now I'm left with 1 over 4 factorial. And 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24. So 1 over 24. And that would be my final answer for the remainder of this problem. It will be 1 over 24. Any questions about any of these steps? Or anything I need to clarify? Yeah, I'll go ahead and ask again while y'all are going through the work. Is there any questions that y'all have about my work or any stuff that you would like for me to clarify?
So I jumped in a little late, but how'd you know to take the fourth derivative?
Hmm. So I know how to take. I know that I'm taking the fourth derivative, Davis, because I was given in the problem that I am approximating with the third order Taylor polynomial, and so because I know I'm working with the third order Taylor polynomial, that means n is 3 for this problem, which means in general, when I'm trying to find m, I find m by looking at the n plus 1 derivative and bounding that guy. And so that's why I know I need to take the fourth derivative of the function, because since n is 3, adding 1 to that means I need to take the fourth derivative. So that's how I know that.
Okay, thank you.
Welcome. Any other questions, y'all?
Was the bound of 1/2 to 3/2 given to us, or did you?
It's supposed to be given. To be quite honest, Zach, I forgot.
Okay.
It was supposed to be here at the very beginning. I forgot until midway when I realized, oh, we need an interval to work with that.
Sounds good. I just didn't know if I missed something.
Nope. That is literally because I forgot. Any other questions? All right. So, see something in the chat. To answer that chat, yep. That is something I do plan on talking about, is using a power series to get an integral for that. So what I plan on doing now is I want to talk about series. See you in the chat. To answer your question, I plan on posting the recording on Discord. And I'm hopefully to get the recording done by tonight and get it uploaded. That is my goal. So but what I plan on doing right now is start with regular series now after this, and then upgrade to power series and Taylor series afterwards for us to work with. So that's kind of my game plan for that. So that said, let's talk about normal series that we get to work with. So at the beginning of this unit, we learned the rest of the series tests, the comparison tests, the alternating series test, and the ratio and root test. So before we dive into problems, what I would like to do is to discuss when to use each test for that we talked about in this unit. And the first test I want to talk about is a comparison test. And this can be either LCT or direct comparison test. Both either or will have the same criteria as to when would I like to use this test. So when would I use a comparison test to check the convergence or divergence of a series? kind of two ways for me to discern whether or not I need to use a comparison test is a couple of things. One, and as a dead giveaway, is if the terms look like a rational function. And so some examples of what I mean by that are some like this. K cubed over k to the fourth minus 7k squared minus 1. If I ignore the series right now and just kind of looked at that, at the terms themselves, they kind of look like a rational function that I worked with before. The k cubed over k fourth minus 7k squared and all of that. Now, when I have this, the way that I'm going to form the series that I'm going to compare with is I'm going to take the highest order term in my numerator and take it over the highest order term in my denominator. So for this particular example, it would be k cubed over k fourth. K cubed because that is the highest order term in my numerator. K to the fourth power because that is the highest order term in my denominator. Simplify. I need to read. That needs to be a k. And that helps me form the series that I want to compare with. So when I'm solving a problem and I think to myself, okay, when should I use a comparison test? One of the things I'm looking for is, hey, if I ignore the series at that point, does it look like a rational function in the series or something like that? The second case or scenario that kind of tells me I might want to use a comparison test for the series is if the terms look like an algebraic function. And what I mean by an algebraic function is it's very close to your rational function, but it could have something extra there, like taking a square root or a cube root or something like that. So one example would be like this, where in my numerator I have square root of k cubed plus 1 over k fourth minus 7k squared minus 1. If I ignore the fact that I'm working with a series and I just look at the terms themselves, it looks like an algebraic function on its own. Why algebraic? Because it looks like a rational, but I have a square root or extra there. Like before, I'm going to form my new series I'm comparing with by taking the highest order term in my numerator and the highest order term in my denominator. So for this case, that would be k to the fourth. The thing to be careful though with the square root of blah is that my highest order term is not k cubed itself. Because it is inside that square root, I do need to consider the fact that it is inside the square root. And so because of that, the highest power would be k to the 3/2 power for that. Again, simplify as much as I can. 4, that will be 8/2, so I should have 5/2. And that'll be the series I compare with. Now, for both cases 1 and 2, note that after simplifying, the series that I got to compare with are P series. In the first example, that one will be a divergent P series because P is 1. Second case, that will be a convergent P series because P is 5/2. I'm doing that on purpose because when I'm doing a comparison test, I want to compare with a P series test or a geometric series. Because if it's a P series, I have a specific test from before that I can use to check for convergence or divergence of that series. Geometric series, I want to do that so because I have a quick test to discern if it converges or diverges. In the third time, where I would like to use a comparison test, is if it is close to a geometric series. So the sample there would be 1/2k plus 1, for example. Note that I cannot use geometric series tests right off the bat because I have a +1 term in my denominator. So because of that, this series I got, can't use geometric series test on. But it's pretty close to that. Because it's pretty close to that, the series I'm going to compare with will be the geometric series, as if I didn't have that extra ding that does not make it a geometric series. So for a comparison test in general, these will be the 3 candidate for times when I would prefer to use it for this particular moment. So I'm going to stop there and see if y'all have questions about anything I need to clarify about when I would use a comparison test for that.
So anything in pink is what you simplified that function decided to be? Okay, just want to make sure.
Yep, everything in pink is explaining what I would compare to. If it's close to a rational or a algebraic, my plan of attack, take the highest order term of the numerator, take it over highest order term of the denominator, and go from there. Keeping in mind that if you do have a square root over it, your highest power will not be just the thing inside that cubed power, because you do have to also incorporate the square root on top. And also if it is close to a geometric series for that. So with that, let's try a plan of attack for some of these problems that I would use comparison test on. So here's the first problem. Let's see if I read this correctly. Yes, I did read it correctly. So let's do this on the 4 minus sine of k squared over 3 to the k power 4 yes. To give emphasis of where I chose that from, this is from the spring 2019 exam. And this is multiple choice theory. Let's give myself a little bit of room. So here's how I'm deciphering and thinking about it when I see it. First thing that comes to my mind here is I see that 3 to the k power. Now, because of that numerator, I can't use a geometric series test right off the bat. I'll have to work my way up there. But I am very close to 1. So that tells me that the series that I will compare with eventually will involve the 3 to the k power. I am going to include the 4 because my thought for this again is have that 4 in there. Yeah, I could get rid of that and do 1 over 3 to the k that I'll be working with and comparing with. But I'm keeping that in there right now because 1, that 4 is not dependent on k, so I can take it outside of my series and work with that. I'm also keeping the 4 in there right now for how we justify it a little bit later on in this problem. But just note that what I'm going to do is I am going to use 4 over 3k as the series I'm comparing with. Now, for a comparison test, 95% of the time you would like to use limit comparison test over direct comparison test. The only time where you would want to use direct comparison test over limit comparison test is if you have an inequality that you can work with. And 99% of the time, if you have a trig function, like I do have with this sine squared, I want to use a direct comparison test. Because with trig functions like this, I can't get an inequality from that. So just to recap, 95% of the time, I would like to use limit comparison tests. The only time I would want to use a direct comparison test is if there's something in my terms of the original series where I can have an inequality that I can exploit. And because I see a trig function, particularly that sine squared k, that tells me that I can exploit that and get an inequality. So I will be using direct comparison test here because of that. So let's start going over the solution. First thing to note, because of that sine squared, sine can never get larger than 1. So because sine cannot get larger than 1, sine squared can also not get larger than 1. Only main difference is it cannot be smaller than 0 because of that. And so starting from that and starting inequality, what I'm going to do now from this step, I'm going to try to eventually get to, let's erase some of my highlights so I can rewrite. There we go. I want to eventually work backwards to get back to the terms of my series. So I'm going to start with that inequality, and I'm going to look at that series and say, okay, I want to eventually get a 4 minus sine squared of k over 3 to the k power over there. That's going to be my goal now. First thing I'm noticing is that in front of the sine squared that I know the inequality for, I have a minus sign up front, which tells me that the first thing I need to do is to multiply everything by -1. Because I'm multiplying by -1, note that I am changing the order to inequality because of that. So because I am multiplying everything by negative, instead of a less than, I flipped it, and now it is a greater than. Negative sine squared of theta, or x, not theta, greater than or equal to -1. From here, I'm going to now more hone into this part of the inequality. And I'll see if the other part will help me later. But note that while I'm doing the remainder of my work, I'm going to be more focused on this part. I'll still do work on that -1 portion of the inequality. But note that I will be focusing my work here. Okay. Now next step. I have the negative sign of square root of k appearing in my inequality. I now need a 4 to appear. Well, in my original terms, I have 4 minus the sine squared of k. So what that tells me is that for me to get to the terms of my series and get that numerator, I'm going to add everything by 4, giving me 4 greater than or equal to 4 minus sine squared of x greater than or equal to 4 plus -1, so a +3. Let's write that bigger. And here I am almost done. Now I need to incorporate the 3 to the k power. That is always positive. So I'm going to do the 3 to the k power over here, giving me now an inequality of 4 over k cubed less than or equal to 4 minus sine squared of x over 3 to the k power over 3 over 3 to the k, so 1 over 3 to the k minus 1, which is always positive for that. So I want to pause here before I keep going and see if anyone has any questions right now.
Yeah, why is it 1/3 1/3 to the k minus 1? Not just 1/3 to the k.
Because I have a 3 in the numerator, when I added the 4 from the -1, giving me a 3. So in my numerator, I have a 3 to the first power over 3 to the k. Oh, that's 1/k. Thank you. Oh, no,
Yeah,
hold
I
on. That
thought
is
that
k
was
minus
really
1.
funny.
Sorry, that's still k minus 1. Because you can think of it as I killed off the 3 in the numerator and subtracted off that 3 to k minus 1. So it should be k minus 1 now.
Okay, I think I get it. If not, I'll just
Yeah.
go back and watch the recording.
That's you. Let's do the work here. So yep, should have a k minus 1 instead of a 1 minus k. Because I'll be subtracting k to 1, get k minus 1. That will be in the denominator, giving me a k minus 1 to denominator. So that's what we got, k minus 1 here.
Okay, I think I get it.
Okay. Any other questions, y'all?
One question I had was for the sine squared, is that sine squared of k or sine squared of x?
Thank you. It should be a k. That is a time where my students in this chat can attest that I said this before. There's a time where I say I cannot read. This is a time where I cannot read. So instead of a s, that should all be a k. So thank you for catching that. Those should be k's. So thanks. Any other questions? Okay. So here's the other reason why I wanted to keep the 4. Because in the work, to force that inequality back, I needed the 4 in there. So that is why in the series I'm comparing with, I did include that coefficient of 4 with it. Because as we're marching on going through that work, I am working here. I have that coefficient of 4. Now, we have this main inequality to tell us which ones we're focusing on more. Let's ask yourselves what we're trying to do. Here, if I use this, 1/3k minus 3 to the k minus 1 power, well, that'll be a geometric series, which would converge because r will be 1/3. However, for direct comparison tests, if the series you're comparing with, if the terms of the series you're comparing with is smaller than the terms of the series that you don't know anything about, then you want that to diverge in order to conclude divergence. But with that upper inequality, I now have a geometric series where r is 1/3 less than 1. And the important thing, I have the less than preserved. So in your notes, you've seen AFK and BFK in there. There's your inequality for that. And this is why 95% of the time you want to use limit comparison tests. Because a big hiccup of direct comparison tests is that you do actually need to show us that inequality. Either AFK is less than BFK, and then the series with BFK as the terms converges, or AFK is bigger than BFK, and the terms of with BFK diverge, which is a lot more difficult to work with. And so that's why the only time I would use direct comparison test over limit comparison test is if I have something in my terms of the original series where I do have an inequality for. Here, because I did have a trig function, I do have an inequality right off the bat, which tells me that for this particular problem, this is a case where I would use direct comparison test instead of limit comparison test. But 95% of the time, you would want to use limit comparison test for checking convergence or divergence.
If this was a free response on an exam, would we have to show the work of how like we do it was how we got our BK?
I think if you just say, here's your BFK, and then you have it appear when you're verifying the inequality, you should be good to go. Keep in mind that, keep in mind that for direct comparison tests, you do need to show that inequality. So what I don't want to see is if you did show, oh, 4 over 3 to the k power is less than that terms, and that converges, therefore the series converges. I'm like, nope, that 4 over 3 to the k is where it's not supposed to be. So you can't use direct comparison test to show me that. That's what I more care about.
I think I'm a little confused here. So that B of K is greater than our A of K. And so what does that tell us about the series?
So keep in mind that for direct comparison tests, this is why we need to do yes. And I'll put an and here and capitalize to emphasize. For me to use direct comparison test, I need 2 conditions. If you showed me that AFK is less than or equal to BFK and the series you compared with converges, then what direct comparison test tells you is that the original series will converge. And so that was why I need to show this inequality here, because the terms with the 4 over 3 to the k power, that is a geometric series where factor out the 4, absolute value for r is 1/3, which is less than 1. So the series I'm comparing with will converge. And so there's piece 1. That inequality in the pink star is piece 2 for me to use direct comparison test to show convergence. So that's why I need that inequality if I was doing direct comparison test.
So if the B of K diverged to the second part, would that just not tell us anything about it? or tell us that the AFK converge? Or sorry,
Correct. Correct. If you've got diverges here for the series you're comparing with, then that means I do need to change the inequality I wanted to show. In that case, the inequality that I did want to show in that scenario would be that the terms of AFK are larger than BFK. So if I note that the series I'm comparing with diverges, then the inequality I want to show is not AFK is less than BFK, but the opposite, that BFK is smaller than AFK. And if I have both of those, then I can say diverges. However, if I had that inequality in red, I did my work, and I got converges, then the conclusion is, I don't know. I would have to do something else if that was what happened. So for a comparison test, if you already know that the series you're comparing with diverges, and if you want to use direct comparison tests, then that means you need this inequality to finish up your conclusion for divergence. If you don't have that order, but instead say AFK less than BFK in that scenario, then you can't say anything for that.
So should we almost do step 2 first to see if BFK converges or diverges, and then work back and make our, or make sure that our
Right. So typically what I would do is I started off by writing the series in pink just to know this will be the series we work for. But typically what I would do is I would start with the work in blue and see what I do here, and then say, okay, here's my inequality. So that is the series I'm working with or comparing with. Would that be convergent or divergent? And see if it makes sense for a direct comparison test. Keep in mind that this is the main reason why direct comparison test is a lot harder to work with than limit comparison tests, because it is very sensitive and, to work with. There's a lot more we have to keep track of and to verify, which is why the only time I would use direct comparison tests is if there's something in the terms of my original series that I can use to form an inequality right off the bat. Otherwise, I would use limit comparison tests immediately.
Thank you.
You're welcome. Any other questions about this problem in particular? I am going to move on to another comparison test problem to kind of show how we do that in general. Okay. So here's the net series I'm going to work with. You want I know where I got this series from. Oh, well, let me rewrite you since a lot got erased by the moving. I got this from fall 2019. For your response to 3. Now, here, if I was looking through it, I would use a comparison test again, because let's go back to when I would use it. One of my ways that I would use it is if the terms look like a rational function here. In this scenario, the terms do look like a rational function. So here I'll be more inclined to use a comparison test. However, there are no terms in that series that I could form an inequality right off the bat. So because of that, I will be using limit comparison test here, because it looks like a rational function and there's no inequality that I can use right off the bat. So because of that, I'm going to use limit comparison test here. The series that I'm going to compare with is going to be formed by taking the highest order term in my numerator and defining it by the highest order term in my denominator, giving me sum k equals 1 to infinity of k. That should not be equal. I'll write compare with sum k equals 1 to infinity k over k squared. Simplify, leaving me with 1 over k. And so before we go any further, one thing that I like to do now is I like to check, see if the series I'm comparing with, I know converges or I know diverges. So if I took the highest order term of my numerator, highest order term of my denominator, I got a series with 1 over k. So will that series converge or will that series diverge? And in particular, I'm referring to the series of 1 over k.
Will that diverge?
Okay. What diverge?
I would say because it's a p series with p equaling 1.
Bingo. It's a p series where p is 1 and our condition for divergence for a p series is that p is greater than or equal to 1. Very good. Note, I'll write here below, that for this series in particular, this is a special series, so harmonic. So if you wrote divergence because of harmonic, I understand immediately what you're talking about as well. And that will also give you full points for knowing why the series you're comparing with diverges as well. So for this particular example, either or will get full credit for that. So, and I'm so sorry, P will diverge because less than or equal to 1. I think I said greater than, but divergence criteria is less than or equal to 1. So that was me saying something wrong. So 1 less than or equal to 1 diverges. So that's why it diverges. Okay. So now we use limit comparison test to check for if we can use it. Recall that for a limit comparison test, what we're going to do is we are going to take the terms of the series we don't know nothing about and divide it by BFK, or the terms of the series I'm comparing with. Now, this is an extra step that I typically do, but I like to do this extra step because it helps with the work. I always think of this as taking 1 over, or the reciprocal of the terms of the series that I'm comparing with, and then multiplying it by the original term, by the terms of the original series. Doing that, I get 1 over b of k. Keep in mind that b of k is referring to the terms of the series I'm comparing with. So 1 over b of k, or the reciprocal, will be k. I'm writing the 1 on the denominator on purpose to illustrate the next step. Multiply by the terms of the original series. Multiplying two things together, which means that multiplying the numerators, multiplying the denominators, that gives me limit as k goes to infinity, k times k plus 3 over k squared plus 4k plus 1. I need to, there we go. I need to distribute that k over my terms of the numerator. And doing that will give me limit as k goes to infinity of k squared plus 3k over k squared plus 4k plus 1. Valuing that limit, what am I going to get if I evaluate the limit of that guy?
1.
1, right. Rational function, highest power to the numerator, same as highest power into the denominator. So our tools for Cal 1 says that limit would be as if I'm reading the coefficients. So let's summarize what we did. What we did was we showed that if I took the limit of the terms of my original series and divide it by the terms of the series I'm comparing with, I get 1, which is a positive finite number. And so what limit comparison test says is that whatever is happening to the series I'm comparing with, that will also happen to the original series. So if the series I compare with converges, my original series would converge as well. In this case, because the series I'm comparing with diverges, that means the original series will also diverge now. So let's summarize that at the bottom to write a conclusion for that. So since L is equal to 1 by our work, and it is a finite number, and we know that the series that we are comparing with, we know that it diverges. Then what we can conclude is by the limit comparison test, my original series will also diverge. So my original series being the sum of k plus 3 over k squared plus 4k plus 1 diverges as well. So any questions about any of my work here? Or anything that y'all would like for me to clarify?
So what does it mean if L equals infinity?
Good point. If I got that L equals infinity, then I better have that the series I'm comparing with diverges. If I get that the series I compare with converges, but I somehow got that L is equal to infinity, then what that would mean is that I actually messed up somewhere. I'll need to check for that.
So if L equals infinity, that means that A of k also diverges.
If I have diverges here, yes, for the BFK. If the series I compare with converges and I get infinity, then I need to go back and double check my work for that. And that's
Okay,
actually a
got it.
good, yep. And that's actually a good question to ask. Similarly, if you get that L is equal to 0, then you better have that the series you compare with converges, because standard limit comparison test would say that your series will converge. However, if the series you compare with diverges and you get that L is equal to 0, we should go back and double check our work. But typically, I do want L, but if L is between 0 and infinity, then limit comparison test says whatever's happening to the series I compare with will also happen to the original series. Like I said, Fritz, thanks for asking, because that is a good point to make. What if L was infinity?
Couldn't you also use the direct comparison for this one?
You can, however, that will be more difficult. Because unlike with the previous problem, I do not have an inequality right off the bat to work with to help me exploit. And majority of the time, that inequality is hard to get, and I could have hiccups. So that's
Okay.
why 95% of the time, if I have a choice, I would prefer to use limit comparison tests.
Okay.
The only reason why on the previous problem we did use direct comparison tests is because of that sine squared of k. That had an inequality that we already know that I could exploit.
Okay. Yeah, makes sense.
Any other questions, y'all? Okay.
Isn't there, so you said that the harmonic series, we always know that the harmonic series diverges. Isn't there a series that we know always converges in this similar form?
Alternating harmonic series would be the case.
Okay.
That's the only.
Professor, your audio's out. We can't hear you.
How about now?
Now you're good.
Okay. Yeah. Alternating harmonic series, to reiterate, that's the first thing I can think of that I know automatically will converge. And that's by alternating series stats.
So if we have a alternating harmonic series, do we have to show that show the alternating series test, or we can just say this is
I don't believe so, because one, I think Dr. Berg covered that in her video. Because that is the pinnacle example of a conditionally convergent series, and is also a well-known series. So I think
where's that form? Is it with the -1 applied there?
Yep.
Okay.
the only thing different I would do with my harmonic is instead of -1, -1's to the kth power.
Okay, thank you.
You're welcome. All right. Any other questions, y'all? Speaking of alternating series, nest test, alternating series test. The when to use for alternating series test is short, sweet, and to the point. I would try to use an alternating series test if my series is written of this form, where I have some positive terms and then an alternating term, the -1 to the kth power or something like that. If I have one of those things, then I would probably be using an alternating series test for that. Let's recap how to check for alternating series tests. One, the thing you need to know before you can use alternating series tests, you do need to check that BFK, or that positive term here. You need to check that that is non-increasing or decreasing. Otherwise known as decreasing. And the second condition we need to check is that if I take that limit, it goes to 0. If conditions 1 and 2 are satisfied, then what the alternating series test says is my series will converge. And with that, I'm going to make a very quick remark now about that. Here for alternating series test, I said that the series will converge if I satisfy conditions 1 and 2. I said nothing about divergence of the series. That's not, I didn't skip that. I did not talk about divergence on purpose. Because just like with the divergence test, if One thing about divergence tests we all learned is even if I don't show that the limit of the terms or show that the limit of the terms go to 0, that does not mean my series converge. It means divergence tests cannot be used here. Same thing is true with alternating series tests. If you do not satisfy conditions 1 and 2 or 2, that does not automatically mean the series diverges. It just means I cannot use the test for yes. So I'm going to make that as a remark. If those conditions 1 or 2 are not satisfied, then it does not necessarily mean that the series diverges. What that means is I cannot use the alternating series test on this problem. And it does not necessarily mean series diverges. It means that we cannot use alternating series tests. And I want to emphasize that because I'm going to guarantee that someone on test 3 is going to try alternating series test. They realize, oh, conditions 1 or 2 breaks, I cannot use it. Therefore, it diverges. That is not the case. Just like with the divergence test, if you show that the limit of the terms equals 0, I can't conclude convergence. For the alternating series test, if 1 or 2 does not satisfy, that does not necessarily mean that the series diverges. All that means is alternating series test is inconclusive, and I need to try a new test. Any questions about that or anything I need to clarify? Okay. So with that, I'm going to do a problem with alternating series. And our goal is we're going to determine if the series converges or diverges. So here's the terms of the series that we're working with. The -1 to the k power over k to the 3/4 power. Just like before, I did pull this from my old test as well. And for reference, I got that from the first free response problem for yes. Okay. So first thing I'm going to do to make it clear what BFK is I am going to move that -1 to the k power, and I'm going to move it over to multiplied by 1 over k to the 3/4. And that will act as my BFK for this problem. So let's check my conditions. First condition I need to show that 1 over k to the 3/4 is decreasing for this guy. Now, in general, the way to show decreasing for P of K for alternating series test is something similar that we did for the integral test. And that is, I'm going to define a function that is married to B of K, and it is married to B of K because all I did was I replaced K with X. Because I have a function, I also have to specify its domain. Its domain is 1 to infinity. Why 1? Because the series begins at 1. Why infinity? Because the series goes to infinity for that. And so what I'm going to do, like what we did at the beginning of this review session, I'm going to use the first derivative test to help me. So what I now want to show is I want to show that the function f of x itself is decreasing. And the reason why I'm marrying it with a function is because we can use a tool from Cal 1 to help us. We can use the first derivative test. Because first derivative test says that if the derivative is negative, then that means that my function is decreasing. And because f of x is married to B of K, because all I did was I replaced the x for K, if f of x is decreasing, so will B of K as well. Now, before I take the derivative, are there any questions about that or anything I need to clarify about that? Okay. So let's take that first derivative. So I'm moving the 3/4 power to the numerator on purpose because that means it becomes a power rule problem, not a quotient rule problem. And power rule says, take the old exponent, make it a coefficient, times x, old exponent, subtract by 1, giving me negative 3/4 x to the negative 7/4 power, or negative 3/4x to the 7/4. Now, keep in mind that all of my numbers or all of my values for x are all positive numbers. That means no matter what I plug in for x, it will always be positive. Denominator has the coefficient of 4. So denominator will always be positive. But in my numerator, I have a negative sign. So what that means is, if I plug in any number in my domain, I will always have a negative number for that. So for all x in my domain, which is 1 to infinity. So that means f of x is decreasing. And because f of x is married to B of K, that means B of K is also decreasing. So let's summarize that below. is that by the first derivative test, one over s to the 3/4, which is the function we have, is decreasing. So b of k, which is 1 over k to the 3/4, is also decreasing. And that is my first criteria for me checking to see if I can use the alternating series test. So condition 1 is satisfied. Before I move on to check condition 2 for alternating series tests, does anyone have any questions about this step or anything I need to clarify? Okay,
Oh, sorry, I did have a question.
go for it.
I can't remember if this was in one of her videos, but did she show a way to show that it was decreasing using inequalities?
She did, but usually that's more difficult.
That's what I was thinking about. I couldn't.
Yep. Yeah, so you could show decreasing by using inequality. In fact, I believe if you look that solution up for the old free response, my guess is that's how Dr. Burr wrote her solution for that problem. However, typically with those inequalities, those are a lot more difficult to justify. So to avoid that difficulty, I'm explaining the fact that f of x is a decreasing function, and because it's mirrored with b of k, I can use that to say, because f of x is decreasing, so must b of k as well. That's a good point. Any other questions? Condition 2. Condition 2 is going to be very short, sweet, to the point. I'm taking the limit of b of k. Limit as k goes to infinity of 1 over k to the 3/4 power. Denominator is getting super large. Numerator is not changing at all, which means that the limit is 0. Which means condition 2 is automatically satisfied. So by conditions 1 and 2, I now know by the alternating series test that my series will converge. So let's write that down. By the alternating series test, I now know that my series -1 to the k power to the k 3/4, I know that it converges. However, because this is an alternating series, the next question then becomes, does the series converge absolutely, or does it converge conditionally? Quick recap for what this means. For me to check if the series is absolutely convergent, I want to take the absolute value of each term, and what I'm going to do is, if I do that, do I still have a convergent series, or does that actually make it divergent? So if a convergent series stays convergent if you take the absolute value of each term, then I say that the series is absolutely convergent. However, if I take the absolute value of each term and I got that the series now diverges, then I say that my original series is conditionally convergent. And because it is alternating, that is something I need to do. I need to vouch and see. I know it converges, so does it now converge absolutely, or does it converge conditionally? So that'll be the next thing I now need to check. So I now take the absolute value of each term. K to the 3/4. Taking the absolute value of each term will mean that I get rid of the -1 to the kth power and only leaving me with 1 over k to the 3/4. And now we need to check if that series converges or diverges.
Diverges by P series, right?
Yep. What's my P in this case?
3/4.
Bingo. This diverges, as Davis mentioned, because it is a P series. The P is 3/4. That's less than or equal to, that's definitely less than 1. And so by P series test, we know that this is a divergent series. And so overall, with my original series, because the original series does converge, but my other series diverges if I take the absolute value, so that means my series is conditionally convergent. So I'm going to summarize it down below. Since my original series converges, but the series, if I remove the -1 to the kth power, because that diverges, then my original series converges conditionally. Let's keep you in green. There we go. Overall. Any questions about that and how I got conditionally convergent? Okay. In that case, I'm going to move on to the last 2 tests, and I'm going to group them together in one, which is ratio and root test. And let me spell test right. It does not end with a K, it ends with a T. And I'm grouping them both together because they're very similar to each other. So, first, when am I going to use either or? For ratio, I will use ratio tests. If I see a factorial, that automatically says, okay, do a lot of cancellation, so I want to use ratio tests for this guy. The other time where I would also use a ratio test is if you could do it with a K power as well, but typically you would do it with a K power if it is K power you see, but not on every turn. So if I see a K power somewhere, but say not a K power in every single term, even if I don't see a factorial, I'll be more inclined to try to use a ratio test rather than a root test for yes. And the reason why is, yep, the root test will cancel out some of those K powers, but they don't have a number or K raised to a 1/K power. And now you gave me indeterminate power that makes it harder to work with. Which is why for root tests, I will only use the root test if every single thing in my series is being raised by a K power. That would be when I would use a root test, because root test means I'm taking a K root, which means I can get rid of the K power from that. So with that, let's do a problem with one of these two. So let's say this will be the series I want to check convergence and divergence for. Can I give reference? This is the old fall 2019 exam. And this is the second free response problem. So let's tackle. Because I see factorial terms in my series, and I do see a K power, but not a K power everywhere, that tells me I am more inclined to do the ratio test here. And so let's go through the solution. One thing that I do with ratio tests is bookkeeping becomes very useful. So what I am doing on the side is I am keeping some bookkeeping to help me keep track of everything. In particular, I am going to write down the reciprocal of A of K. And the reason why I'm writing down the reciprocal of A of K is because for ratio tests, what you're calculating is the limit of the ratio of a of k plus 1 over a of k under the absolute value. Leaving it like this is usually really nasty and awful. So one way that we can rewrite that in order to simplify our work is to rewrite it as you're taking the reciprocal of a of k and you're multiplying it by a of k plus 1. And I like that a little bit better because that means when we're taking that limit actually, instead of having to divide and keep track of what's going on, what we can do then is we can do some cross cancellation from that. So that's why I'm copying out the reciprocal a of k plus 1. So that means, and let's emphasize the k plus 1. And that means wherever I see a k, I'm replacing it with k plus 1. So k plus 1, 5 to the k plus 1 power divided by, and a of k, I have k factorial replaced with k plus 1. So k plus 1 factorial times a k plus 1 factorial in my denominator. I've now done my bookkeeping, so now I'm ready to take that limit that we had to for ratio tests. So L is equal to the limit as k goes to infinity of the reciprocal of a of k times a of k plus 1, which is equal to the limit as k goes to infinity. Copy down now that we've done bookkeeping, the reciprocal of a of k factorial times k factorial over k times 5 to the k power times a to the k plus 1 term, which since we did our bookkeeping, we get to copy down. K plus 1 factorial, k plus 1 factorial.
Could
And
you
now
write
our-
that denominator as k plus 1 factorial all squared? Like, is that a thing you can do?
I mean, you can. However, that will, I think, make the cross cancellation a little bit harder if you leave it like that. So
Okay.
Technically, you could group it all as k plus 1 factorial, all of that squared. However, I'm explicitly leaving it out on purpose because it'll make it clear what cross cancellation I can do.
Okay.
Mentioning that, let's start talking about cross cancellation because at this step, that's our goal now, is we wanted to see if we can start canceling some terms. So from here, what can I cancel out? Or what is something I can do to simplify this guy?
You can simplify the k plus 1 factorials to k plus 1 times k factorial.
Okay, you're exactly right. So to summarize what Zach was mentioning, he's using this property of factorial, which is correct. And what that will do if I do that for the denominator, I'll copy that down. And write it down here. Copy. Let's paste. Come on, technology, don't fail me now. Thank you. Perfect. So let's do that edit now. K plus 1 times K factorial times K plus 1 times K factorial. Okay. So after doing that rewriting, what can I do now to help simplify this limit?
We can do 5 to the k times 5 to the 1.
Okay. Correct. So let's do that rewriting. A little greedy. So that's correct. And now what else can I do? In particular, can I do some cancellation?
Yes, you can cancel out both your k factorials and your 5 to the k. And
Bingo.
also one of your k plus 1s.
Bingos. And that's our end game, usually when I'm rewriting. I want to try to cross cancel terms right from the get-go. Quick note. This stuff is really good and good to go. If y'all wanted to, y'all could have begun the cancellation of this stuff as well. But explicitly writing it out is also fair game. So if you do the cancellation like that, or do what Zach was mentioning and start rewriting some stuff and then cancel afterwards, they will both be correct. So I want to emphasize that. So let's see what's left behind. Limit k to infinity. Absolute value. Only thing left in the numerator I see is a 5. Only things that survive in the denominator are k, k plus 1 being multiplied together. Everything
Where's that
inside
other
here.
k at? All I see is the k plus 1.
So that other k is coming from here.
Okay, I see it. Thanks. I was looking in the purple.
No, you're completely fine, Davis. Yep, that's where the other k is coming from. Now, because everything will be positive now, absolute value is now redundant. Nothing with k in the numerator. All my k's are in the denominator. So if I take that limit, I'm going to get 0, which is definitely less than 1. So with that work, limit is 0, less than 1. From ratio test, what can I conclude now that I did that about my series?
It converges, right? No, it diverges.
You're correct. You're correct the first one, Davis.
Oh, dang it.
No, it's perfectly fine. Yep, but you were right at the beginning. It does converge. If it was bigger than 1, then it would diverge. And then if it was equal to 1, all I could do is shrug and be like, I don't know. But
That's why I always like those sheets, the series sheets.
yep, like I said, yeah, mentioned in class, Davis. That's why we give the sheets to y'all, because we care more about you using it, the test, not memorizing it. So, but now that we have that as strictly less than 1, ratio test will tell me that the series will converge. Since L is equal to 0, which is less than 1, by the ratio test, I want you to be purple. The series converges. And that'll be my final conclusion for that problem. All right. Any questions about that problem before I move on? Just note that due to time, I am going to skip the Taylor series and stuff because someone did ask in the chat to go over Taylor series and power series. So, any questions about my work here or anything I want y'all to want me to clarify? Okay, that's the case. Power series and Taylor series. So, for a power series, keep in mind that for me to have a power series, it is a series that is always in this form. Where I have some coefficient dependent on the index of the series, and then x minus the a k power. In power series lingo, if I say centered at or centered by something, that number, that tells you that it'll be s minus that number, which I call the center. For Taylor series, I'll write here power series. For Taylor series, they are power series on their own. The main difference is my CFK comes from what I would do for a Taylor polynomial. And that should be a k under the derivative. There we go. So Taylor series. So if I say power series, I'm referring to in general a series where I have s minus a raised to the k power. If I'm referring to a Taylor series, my CFK will be, I got that from a Taylor polynomial. So for power series, excuse me, the reason why I want to mention both at the same time is to emphasize that Taylor series are also power series. So all of my properties that I have for power series, they carry over when I talk about Taylor series as well. So in particular, let's do that to talk about some things with that. So for his problem, let's talk about Taylor series. And then we're going to use that to talk about integrating and stuff like that. So here's the problem we're going to do. So for this problem, I am going to use the Maclaurin series for Taylor series, which, for context, Maclaurin series are when the center is 0. So if I say Taylor series, but I'm writing down the Maclaurin series, I am referring to the Maclaurin series. So just keep that in context. So I'll go ahead and give y'all the Maclaurin series for sine of x, -1 to the kth power x, 2k plus 1 over 2k plus 1 factorial in the interval of convergence is any possible real number that I work with. So we're going to be using this guy to help us out. Okay. So step 1, or part A, we're now going to determine the Maclaurin series for sine of pi over x divided by pi times x for this guy. Now, because Taylor series are power series, properties of power series do come into play here. And I'll write down the properties that I need to get this problem down. The first property that I will be using is if I have a composition of two functions and I already know the power series representation of the outside function. So let's say that f of x has power series representation of yes. Then the first property says that all I do differently is I write down the power series for f of x, but wherever I see an x, I replace with that inside function. That will be the first property we're going to use to get the Maclaurin series for sine of that, sine of pi times x over pi times x. The second property that I'm going to be using is if I have some coefficient chilling on the outside of my power series, then I can move that x to the n power over inside to my series, giving me C of kx n plus k. So those are the two properties that I'm going to be using to find the Maclaurin series for this problem.
Will we use these properties for, is this just specific to this problem or
All of them. This is universal.
for Taylor series or Maclaurin series?
All of all of it. So Maclaurin series are a special Taylor series where the center is 0, and this also carries over to power series.
Okay.
So these properties are universal, period, regardless of what I'm doing with power series or Taylor series. So with that, let's get down to business. So first thing I'm going to do is I'm going to ignore that denominator right now because that has something to do with it. Because what I know right now is the Maclaurin series for sine of x. Because I don't have x inside sine, I have pi times x. That's going to act as my h of s in this problem. And so property 1 says for the power series or the Taylor series that I am doing, what I do to get the Maclaurin series for that guy is write down what I currently know for the outside function, but wherever I see an x, I replace it with the inside function. So let's do that now. First, do nothing to here times, write down the Maclaurin series for sine. However, instead of writing an x to the 2k plus 1, I am writing down pi times x to the 2k plus 1 over 2k plus 1 factorial. Okay. Next up, I have that 1 over pi times x chilling on the outside. I'm going to use property 2 to now move it inside of my series, giving me now d sum starting at 0, ending at infinity. Numerator stays the same. But with my denominator, I have an extra pi times x term chilling in my denominator. What I'm going to do now is I make the observation, well, I have a pi times x in the numerator, pi times x in the denominator. I can simplify that, giving me pi x to the 2k power if I do that. Meaning my Maclaurin series for this problem is d sum starting at 0, ending at infinity, -1 to the k power, pi times x to the 2k power over 2k plus 1 factorial. And let me rewrite you to make you a little bit clearer. And before I move on to the next problem to where we integrate, I am going to do one more simplification. And the simplification I'm going to do is with that pi times x. Because inside that, what I wrote in blue, it's all under the exponent of 2k. Before I move on to integrate, what I'm going to do is I'm going to use my property of exponents that says if I have two numbers that are multiplied together, all raised by the power of 2k, that is the same as saying take the first number, raise it by the 2k power, take the second number, raise it by that same power, multiply the results at the end. giving me the sum. K goes from 0 to infinity. -1 to the kth power times pi to the 2k power times x to the 2k power divided by 2k plus 1 factorial. And there's my Maclaurin series for this problem. Now, before I move on, any questions about my work here? Anything I need to clarify?
What's the purpose of doing that with the pi x to the 2k? Is it just a little bit more simple?
Got you. You're talking about why I did this step or the step above? Okay.
The last step is.
Okay. Because let's say I'm integrating term by term, a common mistake is thinking that I am integrating and treating that as an independent variable if I left it inside 2k power. And same if I'm differentiating it. And so I moved it over on purpose like this to make it clear that if I am differentiating or integrating, that pi to the 2k is a constant with respect to my derivative. So I did that extra step mainly because if I am integrating or differentiating, that pi to the 2k is a constant, not the variable I'm integrating with or differentiating with.
Okay.
So you're welcome. Any other questions, y'all? All right. So with that, now what we're going to do is we're going to use our answer from part A to take the definite integral of this guy. And so for gets, I will be using another property of power series. And that is if I am integrating a power series, let's use colors to differentiate the two. If I'm integrating a power series, then what I can do is I can move the integral inside my power series. And rewrite this as sum k equals 0 to infinity of the integral, let's make you blue, of the terms within my series. Now, quick comment. I'm integrating with respect to x. That's C of k, that's just a coefficient with k's in it. So that C of k is a constant with respect to the integral. Because of that, still inside my series, I can rewrite that as moving that coefficients of k out, taking the integral of ds of k here. And the nice thing about this is integral of x to the kth power, that's power rule antiderivative, where I add 1 to my old exponent to give me the new exponent, and then I divide by the brand new exponent. So let's do that. So in general, I will have something like this. And that's how I'll take integrals with a power series. Yes, now if I'm differentiating a power series, it's going to be very, very similar to integrating. Everywhere you saw the integral notation, replace it with the derivative notation. Same process from that. Only difference is with derivative, instead of using the antiderivative version of the power rule, you'll be using the derivative version of the power rule for that. So with that said, I'm going to copy that, our answer from the previous part down, so I don't have to rewrite it, and get to the problem. So we're asked, come on, technology, I want to erase, thank you. Integral of 0 to 1 of sine of pi times x over pi times x dx. From part A, we know what the power series is for that, or the Maclaurin series is for that guy. And because I have technology, I'm going to cheat, copy, move you here, change you all to blue. Get rid of that. Highlight dx from our answer in part A. From our property in purple, what I can do is I can move the integral inside the power, inside the series, and take the integral term by term, giving me the sum, k equals 0 to infinity, inside the integral from 0 to 1 of -1 to the kth power, pi to k power, divided by 2k plus 1 factorial times x 2k power dx. Now, as you saw in that step, I then moved the x to the 2k power on the side. I did that on purpose because now that I've isolated the x to the 2k power, I now know what C of k is for this problem. It is the -1 to the k power times pi to the 2k power, all divided by 2k plus 1 factorial. I'm taking an integral with respect to x. This whole component does not have an x in there. So for all I care about, that's a constant with respect to the integral. So I could take that out of the integral and just integrate s to the 2k power, which is what I'm going to do now. Sum k equals 0 to infinity. My coefficients that do not have an x times integral s to 2k dx. I'm going to use power rule on this guy, which says add 1 to the old exponent, giving me a new exponent, and then divide by the brand new exponent. So for that guy in blue, ignoring the bounds right now, what will that antiderivative be if I did that?
X to the 2k plus 1 over 2k plus 1.
Bingo. Bingo. Thanks, Zach. Exactly right. Zero. Did nothing to the guy in orange. That's a pi. And like you said, x to the 2k plus 1 power over 2k plus 1. Now, this is a definite integral. So I still need to evaluate at both the upper bound and the lower bound of this guy. So let's do that explicitly. Sum k equals 0 to infinity, -1, k power pi 2k power 2k plus 1 factorial. Fundamental theorem of calculus says evaluate my antiderivative at the upper bound subtracted by antiderivative evaluated at the lower bound. Upper bound is 1, so 1 to the 2k plus 1 power over 2k plus 1 minus lower bound 0 2k plus 1 over 2k plus 1. Yes, guy will just become 0 because the numerator will always be 0. 1 to the 2k plus 1 will always be 1 in the numerator, leaving the guy that's highlighted blue underneath to be 1 over 2k plus 1, leaving me with the sum going from 0 to infinity of -1 k power pi 2k power over 3k plus 1 factorial times 1 over 2k plus 1. And that gives me my final answer for that part of the problem. So to summarize, if you're integrating or differentiating a power series or a Taylor series or a Maclaurin series, like in this case for Maclaurin, you're going to integrate or differentiate term by term. And you're going to do that by moving the integral or the derivative inside. Note that you will have some constants that do not have an x involved at all. You can take those outside of your integral and derivative, not outside of the series, but outside of the derivative or the integral. And it boils down to you using power rule inside your series for that. In this case, since we have bounds for an integral, I will be doing a definite integral, which is why we did our work in blue in the next to last step, because I had to do a definite integral there. So with that, I'll scroll up so the entire work is there. Any questions for me or anything that y'all want me to clarify about my work?
I don't really know how much of a question this is, but I think that I understand everything that you do within the problem itself, all the specifics, but I think the bigger picture of these kind of problems with the Taylor series gets a little confusing for me. Is there any way you could do, just explain it's a 3,000-foot view of what we just did?
Kind of explain the big picture idea. Trying trying to have a good way to do that. So kind of big picture what we did, and I will kind of cut off here to kind of do side by side. So what we did was we said, okay, I want to integrate or differentiate the function f of x. Problem is, this function might be awful to work with. For example, in the problem we did, over here, I say if we integrated that using tools from Unit 2, while it is possible, it will be not fun to do. And the reason why is because first you have to do a u sub, where u is pi times x. And then you have to do an integration by parts type of problem for that. I believe Chelsea already left, but appreciate that message. And stuff like that. So sometimes when you take an integral or derivative, it might be awful. What might circumvent that is, oh, well, I know that f of x has a power series, Taylor series, Maclaurin series, or something like that. Here we did Maclaurin series, so I'll keep it as Maclaurin series of blah. And so, which that does not help, so I'll just write that down. See, Maclaurin series 0. Okay. And so what that becomes is saying, okay, yes, integral is difficult, and I want to still integrate that and get something meaningful out of it. Well, I could get something meaningful out of it by replacing the function f of x with its Maclaurin series. With that. And that's nice because this is a Maclaurin series, I can move the integral inside the series and integrate term by term. Giving me this guy. To give me something more meaningful from it. As mentioned, that has nothing to do with variable x. I treat it as a constant, so I take that out. Giving me something that we have here. And then my power rule, evaluate as yes. Nope. So I guess the big picture is taking the integral of f of x is like, okay, that might be difficult for me to do right off the bat. Later on in future math courses, you'll learn that there might be some functions that you try your best to integrate, but try as hard as you might, you're not going to get a good solution. You're not going to get an exact solution from it. So what's the next thing I can do? Well, I know the Taylor series and Maclaurin series of the integrand, so I can get something term by term to try to help me get something more meaningful from that and something that I can work with in future applications. Don't know how good big picture that is, but
That was,
that's kind of how I take it. Okay.
yeah, it was. So for that, our answer down at the bottom, the use.
Mhm.
Is that just, that's us finding the Maclaurin series that fits our sign of X? Is that basically the answer? You're saying?
Right. That series that we got as our answer,
Mhm.
that is representing the Maclaurin series for the integral of sine of pi over x times pi over x if I was to integrate that from 0 to 1. So in other words, that entire whole integral on the left-hand side, I now have represented that guy by integrating term by term as his own Maclaurin series.
Okay.
And the reason why that's pretty powerful is in say a lot of applications, you're not going to have like actual, like, trying to figure out how to phrase it. You're not going to have like an exact function that you'll be working with. And so what your goal is you want an approximation. Well, Taylor series and the Maclaurin series helps you out in that case because it gives you a decent approximation for what you care about, even if you may not know exactly what the function is. So that's sort of a bigger picture for future courses and in terms of how people actually use the Maclaurin series. Say, I may not know what the exact function is or how to work this integral, but I do know a series, and I can get a pretty darn good approximation from that, from working with the series itself. And it's the same idea with the derivative as well.
All righty, thank you.
You're welcome, Zach. Any other questions?
I want to know where we can find the Zoom link for like the recording.
I'll post it later tonight, Manny.
Okay.
It needs to be processed. And probably what I'm going to do, because Zoom is finicky with recordings, I'm probably going to upload it to my YouTube channel
Okay.
that I have, and then just give the YouTube link once it gets rendered.
Okay. Thank you.
You're welcome, Manny. All right. Any other questions, y'all? All right. I don't know about y'all, but it is 8:18. I'm pooped. So with that, I'm gonna end the review session here.
Thank you so much.
Now you're welcome, Sat,
Have a good evening.
too.
Are you going to be stopping in the Calculus Fight Club again?
No.